In this lesson, we're going to look at electric and gravitational fields. Here are the objectives. Essentially what we're going to do in this lesson is we're going to go back to some material from earlier lessons and review that, but do so in such a way that we put the electric and the gravitational situation side by side so you can see the analogies. First, let's start with the electric situation. This is the charges and field simulation from PhET. The URL is here at the top, and I'm going to place a positive charge into the middle of the screen. And remember that a field is a region in space where a force will be felt. So by putting this positive charge here, it creates an electric field around it, indicated by these arrows, where if I were to place another charge, like this yellow sensor, the yellow charge would feel a force. Now, in this case, the yellow charge, the yellow sensor, is a positive test charge. It's small and it's positive. And by moving it around and observing the red vector arrow, I can see that if it's further away, it feels a weaker force, and if it's closer to the positive central charge, it experiences a stronger force. And that's because of the inverse square nature of Coulomb's law. And if I were to take this positive charge out of here and replace it with a negative charge, we would see that now all the arrows have reverse directions, but we still have the same kind of idea. We have a field where the arrows, the vector arrows, are pointing now in towards the negative charge, indicating that that's the direction of the force that a positive test charge like this yellow sensor would feel. And once again, if I move the positive test charge around, I can see that the force that it experiences gets weaker as we get farther from this central charge. If I wanted to graphically represent that vector field, I could draw individual arrows around the central positive charge, and they'd need to be longer, closer towards the charge, and then get weaker further apart. But that gets very messy, and so instead, as we've seen, we can use the conventions of field lines. So we draw field lines emanating from the charge, and they are going to point away from a positive charge. So they're going to look like this, with arrows pointing outwards. Again, the vector field lines, or the field lines, indicate the direction of the force on a positive test charge. And instead, if this were a negative charge in the middle, then the field lines would point in towards the center, because a positive charge would be attracted towards that central negative charge. So I just turn the arrows around. Remember that field lines never cross, and remember also that the density of the field lines, how close together they are, indicates the strength of the field. So here, closer in towards this negative charge, or closer in towards the positive charge, where the field lines are closer, that's a stronger field. We saw a longer arrow on our yellow sensor. So those are the electric situations, and we have two of them here with a central charge, one with a positive central charge and one with a negative central charge. Imagine now, much like this though, we could have a central mass, and because the force of gravity is only ever attractive, if our yellow sensor now was a small mass instead of a small charge, we would be able to draw the vector indicating the force of its attraction to, let's say this was the Earth, and as we move the yellow sensor further out, our small mass further out, that attraction would be less. Again, like we did before, instead of drawing all those vector arrows, we could draw field lines, and they turn out to look exactly like this. The field lines are closer as we get in towards our central mass, or in towards the Earth, indicating that the force per unit mass is stronger, and they get further apart, farther away. So the negative central electric charge situation, this one in the middle here, and the gravitational situation look the same, and the rules of field lines are again the same. No crossing, and closer field lines means a greater gravitational field strength. Let's return now to the simulation, and I've set it up differently. Now I've put a bunch of positive charges in a row and a bunch of negative charges in a row to try and replicate a parallel plate capacitor where I have a positive plate and a negative plate. And you can see that the field arrows point basically straight down in parallel lines from top to bottom. And at the edges here, they curve, and as we go farther out, they curve more. But we have effectively a uniform field. We know that the strength is not changing because the brightness of the arrows is not changing. So the field is uniform throughout here, and we see these parallel field lines going downwards. So to draw the field lines pertaining to that, I'll put my positive plate here at the top, and I'll put my negative plate at the bottom, and we saw that the field was uniform, as indicated in the simulation by brightness. We're going to indicate that with our field lines with equal spacing. So we've got parallel field lines that are not getting closer together or farther apart. Again, remember that the spacing of the field lines indicates the strength of the field, so we want them to be equally spaced. And they're pointing downwards because that's the direction of the force that a positive test charge would feel. And at the edges, we can just curve it, as we saw in the simulation that the field is curved there. Remember that the field strength is the force per unit charge, and we keep saying assuming that that field strength is uniform. So if I were to put a positive 1 coulomb charge down here, I'll call this situation A, or if I were to put it up here, I'll call this situation B. Because the field strength is uniform, the force per unit charge is uniform, and it feels the same downwards force if it's a positive charge in both cases. That's different than the situation up here where the field strength was not uniform. It got stronger as we got closer in. So here, if I were to put a positive 1 coulomb charge in closer to the negative charge, it would feel a much stronger force than it would further away. Alright, so we've got electrical situations here with these single charges where the field is changing, and we've got an electric situation here where the field strength is uniform. We've got a gravitational situation where the field strength is changing. What about one where it's uniform? Well, if we zoom in close to the central mass, in other words, if we get close to Earth, for example, then we have an effectively uniform field, and we can draw it in much the same way that we did with the parallel plate capacitor. We have equally spaced parallel field lines pointing downwards. And again, that has the same meaning. It means the force per unit mass now is the same no matter where you are here. So if I were to put, let's say, a 2 kilogram mass here and a 2 kilogram mass up here, it will feel the same downwards force, in this case 19.6 newtons, in either case, because the force per kilogram is going to be the same throughout. The force per kilogram being the gravitational field strength. Alright, so that's looking at the situations graphically using field lines. Now let's look at definitions and equations. And again, we'll look at the electric and gravitational situations side by side. We know that for point charges, Coulomb's law tells us that the force is given by K times Q1 times Q2 over R squared. And I'm using big Q and little q here instead of Q1 and Q2. And for gravity, there's a very similar looking law, also an inverse square law, that says multiply the universal gravitational constant by the product of the two masses and divide by r squared. Remember that r is the distance from the center of one mass or sphere of charge to the next. So we're always going from center to center. And both of these cases are going to be measured in newtons because they're forces. And I can write a little sub E here to indicate it's the electric force and a little sub G here to indicate it's the gravitational force. Just remember that Coulomb's law is for point charges only, so we couldn't actually use it for that parallel plate capacitor setup that we looked at before. It's for point charges only. So that's force. Field strength is a kind of standardized or per capita force. In the electric case, it's the force per unit charge, in other words, per coulomb, experienced by a small positive test charge placed at a point. So that yellow sensor was our positive test charge, and it would allow us to figure out the force per unit charge at a given point in space. In the gravitational situation, it's the force per unit mass, experienced by a small mass placed at that point. And by doing this, by standardizing, by making the force per capita, if you like, now talking about field strength, we're able to compare points in space and talk about the field strength there without actually even having to place a charge there. So in the electric case, our field strength is measured in newtons per coulomb. So if I have a particular point in space where I know that I have a field strength of 5 newtons per coulomb, then that means if I put a 1 coulomb charge there, it'll feel a force of 5 newtons. If I put a 2 coulomb charge there, it'll feel a force of 10 newtons. If I put a 10 coulomb charge there, it'll feel a force of 50 newtons. So it's a standardized or per capita measure of the force, and therefore measured in newtons per coulomb. And so you can see that for the gravitational situation, it would be measured in newtons per kilogram. So a gravitational field strength of 9.8 newtons per kilogram near Earth's surface means that a 1 kilogram mass will feel a force of 9.8 newtons, a 2 kilogram mass will feel a force of 19.6 newtons, etc. These little absolute value bars that I drew just mean I'm only concerned with the magnitude. If we think about that now in terms of the equations, we need to divide out the charge or the mass of that little sensor that we were using. So I'm going to write electric field as that. The electric field is equal to the electric force divided by, I'm going to choose little q from up here, that's little q here, as my charge of my test charge. And so copying from above and crossing out, I get k times q little q over r squared divided by q is equal to k big Q times r squared. This is the charge on that central charge, the large charge at the center, and the other one, the charge on the yellow sensor, has disappeared. Similarly, for the gravitational situation, I want to take the gravitational force and divide by the mass of the little sensor. That's equal to g times big M times little m over r squared. Big M is the mass of the Earth, for example. Little m is the mass of the thing that's around it, the little yellow sensor. I'm going to divide that out, and I'm left with g times big M over r squared. Once again, we've divided out the point charge or the point mass, and so they're not even really there anymore. We've gotten rid of that, and so the field and the field strength are really just characteristics of the region around the central mass or the central charge. And remember also that they are vectors, so that if I had a negative charge here and a negative charge here, they'd each have fields associated with them, and if I wanted to find the field, let's say at this point right here, I would add those fields as vectors. So the electric field from the negative charge on the left would point down and to the left, and from the negative charge on the right would point down and to the right. And to find the net field there, I'd have to add them using vector addition and get this longer vector pointing downwards in the center. So we have to add them like vectors. And that means that we can also think about charge distributions where we have two like charges or opposite charges and draw the fields associated with them. And they would look like this. And if I had made these two negative charges here on the left, I just have to turn all these arrows around. And that would be the same field line pattern that I would see for two masses as well in the gravitational situation. So that's a review of electric and gravitational fields and a comparison of the two of them side by side.